AQA A-Level Chemistry 2021 Paper 2. Question 1. Coconut oil contains a triester with 3 identical R groups. The triester reacts with potassium hydroxide. Complete equation by drawing the structure of the product. Okay, so all it's going to be is, well, this has bonded to this, and I've got 3 of them, so I've only got really this left. So it's just going to be all of that coupled together. So CH2OH, CHOH, CH2OH. I guess we don't need to show curly brackets around here, it's only there. So CH2OH, CHOH, curly bracket, CH2OH. Name and type of compound shown by formula RCOK. A carboxylate salt. Carboxylate. Hopefully you guys can hear me. Carboxylate salt, and the use is soap. Carboxylate salt, the use is soap. Triester and coconut oil has a MR of that in the equation shown at the start of question 1. R represents alkyl group, that can be written as that, reduced value of N. So what I would do first is 638 triester and coconut oil. Coconut oil contains triester with 3 identical R group triester X potassium hydroxide. Is I'd find out the MR of all of this. So it's going to be the coconut oil triester, 3 identical R groups, this. So I know I've got, first let me add up all the MRs together. 12 plus 16 plus 16 plus 12 plus 2 plus 12 plus 1 plus 12 plus 16 plus 16 plus 12 plus 16 plus 16 plus 12 plus 2, 173. Plus, well then these R groups plus 3 R groups, and then the 15 plus your 14N. Yeah, 15 plus your 14N. Because what I did basically was that I've seen that R group is an alkyl group that can be written as this. The MR of that is 15. The MR of this is 14. So 15 plus 14N, and that represents an alkyl group. R represents an alkyl group that can be written as that. So I can write that as that, 15 plus 14N, obviously just 3 of them, 3 R groups. Then you expand the brackets, rearrange, and you should get 10. Just to show you working, but in the exam we'll show you working. Then it says a 0.1450 gram of sample of coconut oil is heated with that much in aqueous ethanol until all the triesters hydrolyze. Mixture is cooled, the remaining is neutralized by that. Calculate percentage by mass of triester in the coconut oil. So first thing I would do is find out moles of. So coconut oil is heated with this much triester. Aqueous ethanol until all the triester hydrolyzed. Mixture is cooled, remaining potassium hydroxide is neutralized by exactly this much of HCl. So I'll find out the moles of HCl first. Molar concentration and volume. That will give me 1.565 times by 10 to the power minus 3. Then what I do is then I've got then I'd find out the moles of potassium hydroxide. 0.421 divided by the MR of potassium, which is 39.1. 39.1 plus 16 plus 1, and which is going to be 7.50 times by 10 to the power minus 3. Then I can work out the moles of, no, I can't. So I worked out the moles of HCl, I worked out the moles of potassium hydroxide, and that would get me 2 marks. So 2 out of 6, 1/3 of the marks, very nice. Then I'm gonna have to use like a bit of brain power really, because I know that initial amount of potassium hydroxide is 1.565 times by 10 to the power minus 3. No, sorry, is 7.50 times by 10 to the power minus 3. And therefore, the amount of potassium hydroxide used is, well, I know the remaining hydroxide is neutralized by this much of HCl. So all I'm going to do is I'm just going to do 7.50 times by 10 to the power minus 3 minus 1.56 times by 10 to the power minus 3. 565 times by 10 to the power minus 3. That will give me 5.939 times by 10 to the power minus 3. And that is the amount of potassium hydroxide used. Then to find out the ester, well, the potassium hydroxide to the ester, it's a 1 to 3 molar ratio. So now I divide that by 3, and that will give me 1.980 times by 10 to the power minus 3. Then I need to find out the mass of the ester. Moles mass of MR, and mass is the moles times by the MR of the ester, which is 638.0. And then to find out the percentage by mass, it's going to be wherever I get, which is 1.263 over 1.450 times 100. And I should get 87.1%. If you're all like these kind of questions, a lot of students struggle with, including myself. But the first thing you can do is, don't read it hundreds of times or tens of times. Just do the simple stuff like calculate the moles, because you're gonna have to use them later on. So just do that, and then you can be like, okay, I've got 2 or 3 marks out of 6. Now let's actually think about what else I need to do. So find out the moles of HCl, find out moles of potassium hydroxide. Potassium hydroxide is neutralized by the moles of HCl, by this much of HCl. Then do big number minus small number, you get this. Then realize that it's a 1 to 3 molar ratio, so I need to divide that by 3. And divided by 3, I get this much moles of the ester, then times by the MR, and then the mass over the total mass times by 100 to get 87.1%. Suggest why aqueous ethanol is a suitable solvent when heating the coconut oil with potassium hydroxide. To ensure reactants are miscible. To ensure reactants are miscible, meaning they're mixed together. Safety precaution used when heating the mixture. Use a water bath for heating the mixture. Why do we do that? Because, that's the next part, because ethanol is flammable. Hence, heating using a Bunsen burner flame is dangerous. To ensure reactants are miscible, use a water bath for heating the mixture. Ethanol is flammable, hence heating using a Bunsen burner flame is dangerous. State the meaning of fraction is used in the petrol fraction. a group of compounds with similar boiling points. Group of compounds with similar boiling points. Group of compounds with similar boiling points. It says hexadecane cracked at high temperature from petrol. Complete equation to show the crack of one molecule of hexadecane to form hexane C6H14 and cyclopentane C5H. Hexane is C6H14. Cyclopentane is C5H10. But that doesn't make any sense though, because it's not going to add up, is it? Because look, 6 plus 5 is 11. Oh, right, I just checked them out. So you need a 2 here. Again, these are little tricks that they can use to trick you out. The catalyst you use is zeolite catalyst. That's pretty simple. How well you know A1. But yeah, you need to balance the equation by including the 2 moles here. Give a reason why carbon dioxide absorbs infrared radiation. C double bond O bonds are polar. Draw 2 curly arrows to complete the mechanism in figure 1. Figure 1, so it is, I don't know what's going on here, but yeah, that goes to there, then it goes to here, then what happens? Well then, oh right, it's that excess ammonia thing. In this case, it's not that. It's takes acid base, takes a proton, and then leaves like this, and then there you go. A curly arrow there, and a curly arrow there. 2 curly arrows. Name compound Z. It's going to be 2 amino ethanol. And the role of Z in step 2 of the mechanism is a base. It takes a proton. 2-amino ethanol base. 4 marks for all of that. Draw the shape of XNH2 and XNH3. So XNH2, so you got your X and XNH2 H, and you've obviously got your lone pair of electrons. Then XNH3 X N H H H, and because iron has got square brackets, positively charged. There we go. And obviously the XNH3 plus has no lone pair of electrons. So state whether the NH2 bond angle in XNH2 is greater than, the same as, or smaller than that in XNH3 plus. Explain your answers. It's going to be smaller due to the lone pair of electrons, because lone pair repulsion is greater than bond pair repulsion. Therefore, the bond angle would decrease by 2.5 degrees. So draw the shapes out, lone pair XNH2, no lone pair XNH3, include the plus charge, square brackets, smaller bond angle, lone pair repulsion is greater than bond pair repulsion. Question 2.6, bioethanol using alternative fossil fuels. Statement appears on website. The fact that bioethanol is a carbon neutral fuel outweighs the environmental disadvantages of producing bioethanol. In your answer, you should include outline how bioethanol is produced, relevant equation, analysis of environmental impacts. This question, this 6-marker, is a prime example of why you need to know all the content in A-level chemistry. Like, I guess with some subjects, maybe probably all subjects, yeah, you need to know all the content. But like, especially with chemistry, like they can just ask you such a niche topic. This is obviously a year 1 topic, and you know, if you haven't ever even revised this, you're not gonna get probably more than 2 marks. Stage 1. Because remember, there are 3 equations you also have to memorize as well. And that's going to play a big part as well. Stage 1. The names of processes. So, photosynthesis and the natural process in which plants take CO2 from the air. Fermentation, process used to make bioethanol, releasing some CO2. Combustion, process where bioethanol is burned and releases CO2. Stage 2, your equations, your relevant equations you have to memorize. So 6 CO2 plus 6 H2O and C6H12O6 plus 6 O2. Then you've got your C6H12O6 to go into your 2C2H5OH plus 2 CO2, and then you've got 2C2H5OH plus 6 O2 to form 4 CO2 plus 6 H2O. Okay, so the first one's obviously photosynthesis, second one is fermentation, and third one is combustion process. Photosynthesis, plants take up CO2 from the air. Fermentation, make bioethanol releasing some CO2. Combustion, where bioethanol is burned and releases CO2. 6 CO2 plus 6 H2O to form C6H12O6 plus 6 O2. That doesn't look clear. 6 O2. C6H12O6 arrow 2C2H5OH plus 2 CO2, and then 2C2H5OH plus 6 O2 to form 6H12 plus 4 CO2. Then stage 3, analysis of the environmental impacts. Stage 3. The environmental issues. Deforestation, removing land and destroying land which could be used for food, loss of biodiversity, and the main part is the idea of these relevant equations. 6O2 plus 6H12, C6H12O6 plus 6O2. C6H12O6 arrow 2C2H5OH plus 2CO2. 2C2H5OH plus 6O2 to form 4CO2 plus 6H12. The idea that 6 carbon dioxide in, 6 carbon dioxide out. So therefore it's carbon neutral, right? So 6 CO2 given in and 6 CO2 out. However, it isn't actually carbon neutral, and brings it on to another point, the idea that fuel is used in production and distribution. There you go. Stage 1, photosynthesis, a process where plants take CO2 from the air. Fermentation process, where used to make bioethanol, releasing some CO2. Combustion process, where bioethanol is burned, releases CO2. Irrelevant equations. Environmental issues, deforestation, destroying land which could be used for food, loss of biodiversity, 6 CO2 given in and 6 CO2 given out. That's really important. It shows that you are using the relevant equations, you're not just copy and pasting them, you're saying how environmental issues as well. And you're saying therefore viewed as carbon neutral. However, it isn't actually carbon neutral as fuel is used in production and distribution. Question 3. Design a table to record all the readings necessary. Okay, enthalpy of combustion. So what I'd have is temperature, degrees Celsius, initial, final temperature change, delta T. I'll have the mass slash in grams, and then I'll have burner before, burner after mass burned of what I'm working with, heptane. So you need a temperature, initial final temperature change, the mass temperature, initial final temperature change, burner burner before, burner after, mass burned of heptane, mass of heptane burned. Suggest 2 disadvantages of using a glass beaker on a tripod and gauze. Glass is a poorer conductor than copper. Tripod and gauze would reduce heat transfer. So, glass is a poorer conductor than copper. Tripod and gauze would reduce heat transfer. Glass is a poorer conductor than copper. Tripod and gauze would reduce heat transfer. Suggest 2 reasons why the enthalpy is less exothermic. This one's classic question. Heat loss to surroundings. And another one is the idea that incomplete combustion. Suggest one addition to this apparatus that would improve the accuracy of the enthalpy value obtained. Use a lid to reduce heat loss. Question 4. Use figure 3 in the data in table 1 to calculate delta H of 2. Delta H2. So I know enthalpy of atomization of carbon plus 715. And then, so which one's that? Enthalpy of atomization for carbon. And I want to find out the total. So what I'm going to say is enthalpy of atomization for carbon Well, I've got 6 carbons, right? So it's going to be 6 times by 715. I've also got 6 hydrogens, 6 times by 218. Right, so all of this is pretty simple. And because I want to find out delta H of 2, what I'm going to do, delta H of 2, I want to find this. I'm going to say that's Y, and therefore this and this equals this and this. So I'm going to say that then I've got what? So entropy of atomization for carbon, that's easy. Entropy of atomization for hydrogen, that's easy. Bond entropy for carbon, well, I've got 6 carbons, but I've only got 3 of these because look, 1, 2, 3, 4, 5, 6. That's 1, that's 2, that's 3. So it's going to be 3 times by 3, 4, 8 plus 3 times by 6, 1, 2 plus CH's plus 6 times by 4, 1, 2. And basically what I'm saying is that this bit is equal, I'm saying that entropy of 2 equals this bit being subtracted from this bit. So 6 times by 715 plus 6 times by 218, entropy atomization for carbon, entropy of atomization for hydrogen. Then the bond entropies, well then I've got 3 carbon-carbon bonds for CC, and then I've got carbon-carbon double bonds here and here. And then I've got the 6 CH bonds, then 3 times by 348 plus 3 times by 612 plus 6 times by 412, 5352 is this. This bit 6 times by 715 plus 6 times by 218, 5598, 5598 minus 5352, 246. No. I also need to minus the 83 as well, because this way I'm saying this is equal to that, so then minus 83 as well. 163. That's positively charged. Explain terms of structure and bonding why this is more thermodynamically stable than that. The pi electrons are delocalized. Pi electrons are delocalized. So find out that, and bigger number minus small number to find delta H of 2. Name of the mechanism: electrophilic substitution. Electrophilic, is it actually? Yeah, it is electrophilic substitution. There's just so many what's it called, steps. I'm just a bit confused. Complete the mechanism in figure 4 by adding any lone pair of electrons involving each step. 2 curly arrows in step 1, curly arrow in step 2, curly arrow in step 3, curly arrow in step 4 for 5 marks. 1 easy mark, naming the mechanism, and then 4, I guess, slightly harder marks. 2 curly arrows in step 1. On the step 1, I'm going from this to, well, it looks, well, the oxygen is positively charged and this oxygen is negatively charged. So what's going to happen is that so lone pair of electrons here Yeah, any lone pair of electrons involving each step. This partially positive, this partially negative goes to here, and then that goes here. That's what I'm assuming that happens. Yes, but it doesn't happen that direction, sorry. It happens here. So lone pair of electrons here, it happens here because look, there's a negative charge and oxygen there. Negative, there you go. There you go. Then what happens is then this just goes here to the oxygen. Or does it? No, it doesn't. Because if that happens, then I'll be left with OH, O2N. What actually happens is it goes here, then the nitrogen positive charge, and I've got OHH. Then what happens here? This one's pretty easy. There. And one curly R in step 3 and one curly R in step 4. There you go. So you can see some of them are more confident than others. Like step 3 and 4, light work. Step 1 and 2, difficult. Because you need to understand there's oxygen with negative charge, so the lone pair of electrons is gonna tap partial positive hydrogen, then transfer electrons to partial negative oxygen. There you go. And then in this case, step 2, well, if I did that way, well, then I'll be left with OH, O2N. I'm left with OHH. So I have to do the curly arrow this way, and then the O2N is positively charged, and then I also have OHH. So a bit tricky, this part. Definitely a bit tricky. Yeah, this benzene question. First 3 mark on delta H2. That big number minus a small number. This basically 6 times by that, 6 times by that, plus 3 times by that, 3 times by that, 6 times by that. Let's subtract them, you get that. Pi electrons are delocalized. Electrophilic substitution. There you go, there you go. And then there you go. There you go, there you go. And for question 5.1. It looks like an equilibrium KC kind of question. 1 mole of diacetyl mercury formula C7H12O4 is added to 1 mole of water in the presence of a small amount of catalyst. Mixture is left to reach equilibrium at a constant temperature. At equilibrium, X moles of ethanoic acid are present in the mixture. Ethanoic acid complete table 2 by reducing the amount of X of diaster, water, and diol in the present equilibrium mixture. So I've got X moles of ethanoic acid. So in this case, then I'm going to have a half X here. And I'm adding X here. I'm adding X over 2 because remember it's a 2 to 1 mole ratio, that's why it's a half X. But then I'm going to minus X, so 1 minus X, 1 minus X over 2. 1 minus X over 2. Oh, I've done it the wrong way around. That's a bit funny. That's the 2 to 2 mole ratio, so that's perfectly fine. That's 1 minus X. That's 1 minus X over 2. 1 minus X over 2, 1 minus X. X over 2 or half X. For 3 marks, that's pretty nice. That's a really nice question for 3 marks. Then it says, deduce the structure of the diester in question 5.1. C7H12O4. So I've got here, double bond over here, then here, oxygen here, here, the oxygen here, double bond O here. 1, 2, 3, 4, 5, 6, 7. Perfect. So it should, let me draw it out properly like this. There you go. 1, 2, 3, 4, there and there. And then it says, calculate amount of water in mold this equilibrium mixture. So first thing I would do is always construct a KC expression so I can see what I'm working with. It's KC square brackets. So it's going to be concentration of CH3 COOH squared HO bracket CH2 3OH C7H12O4 by moles of H2O squared, because 2 moles of it. Calculate amount of water, so H2O. So all that's going to be is H2O equals square root of CH3COOH, and again that same trick again. That I don't. It's such a sneaky trick. I'll show you guys. CH3COOH. So I'm already given the equilibrium moles and the volume. Well, in this case, it wouldn't work, but sometimes in a question, then they'll give you the volume, and then what you have to do, then most students would just assume they cancel out, but in reality, they won't because KC is here. So you do have to include the volume because it won't cancel out because then KC is not in volume. But in this case, it will. There is no volume. It didn't give us any volume, so it's fine. So you just substitute the moles of them. 0.52 times by 0.273 divided by 0.161 times by 0.971 squared. Square root of that, 0.597 moles. Draw Skeletal formula branch chain aldehyde molecular formula that is as optically active. Bond over here. First thing I would realize is an aldehyde, so carbonyl group at the end of the functional chain, optically active, so I need a methyl group here, carbon here, attached to 1, 2, 3, 4 different groups. C5H10, 1, 2, 3, 4, 5, and your carbonyl group there. Just how you distinguish between separate samples. Use plane polarized light, rotates the plane of in opposite directions. Draw EZ isomers of structure isomers C5H10O that show both optical and geometric isomerism. We've got hydrogen here, hydrogen here, a methyl group here, and then what's remaining is CH3OH. And in this case, because that's E isomer, in this case the Z isomer, and for my CH3 here, for my H here, my H here, and then I'll put CH3OH. There you go. There you go. Question 6.4, draw 2 other cyclic isomers of ether functional group and only 3 peaks and 13C NMR spectra. Can't do this question. Question 7, which functional group does K contain? Look at the periodic table. And 3000 has got a peak, so well, I don't really care about that then. Because this 3000 one, that's pretty much on spot on 3000. That's a CH. Yeah. Or carboxylic acid, but none of these are carboxylic acid, so CH. I don't care about that. Now look at this peak. Well, that's around about 1700, and therefore it's going to have a carbonyl functional group, and therefore yeah, carbonyl because it's got the C double bond O. Which has 3 ways in which the infrared spectrum of M is different from the infrared spectrum of L. Of M is different from the infrared spectrum of L. Well, L reacts with hydrogen in presence of nickel catalyst, so catalytic hydrogenation to give the amine, right? So the peak at 2220 to 26 2260 centimeters to power minus 1 for C triple bond, Sub triple bond and disappears. The peak at 3300 to 3500 centimeters to power minus 1 for NH disappears. Fingerprint region are different. So this is going to disappear and that is going to disappear. I can't do this question H on the mass spectrum. Question 8.1 state the type of reaction in step 1. Well, I'm going from an alcohol to an alkene. So it's a dehydration. Dehydration and concentrated H2SO4 or H3PO4. Yeah, concentrated H3PO4 will be allowed as well. State the regions needed and give equation for step 2 and 3. So regions needed for step 2. Well, I'm going from an alkene to something, and then from this something to a diol. So it's going to be Br2. Or chlorine or thingy or anything. And the equation, well, I've got this double bond here plus Br2. Yeah, plus Br2, and then I'll get this with your OH, OH, OH. No, sorry, Br and your Br. Yeah, that's what you'd get. Step 3 region, well, I'm going from a diol to what it looks like an aldehyde. Step 3 region, sodium hydroxide. Oh no, that's step 4. I need to look at step 3. And then what happens is this with your Br plus 2 sodium hydroxides to give you that with your OH and your OH. And don't remember, plus your 2 sodiums and these 2 Brs. So in the Br. So the step 2 region, Br2. Your alkene plus your Br2 to swap with this. And remember, with these, like, how else would you get these two OH groups? Got the Br, the electrophilic addition one. So then you add your BR, and step 3 region, sodium hydroxide. Well, how do you get from the BR to this? Well, it's a nucleophilic substitution. I'm just replacing it with OH group, the BR with the OH group. Then you do that, 2 NaOH because I've got 2 BRs, and then remember to balance out these two and these two, 2 NaBr, and then you got your OH. Br2 sodium hydroxide dehydration concentrated H+4. Give the name of the mechanism for this reaction. Cyclohexane 1,2-diol reacts with ethane diol dichloride and nucleophilic addition elimination. Nucleophilic addition elimination. Complete the mechanism showed the formation of one S linked to the reaction. So what's going to happen in this case? Well, always that the lone pair of electrons and oxygen, that's partially positive, that's partially negative, that's partially negative. Attacks partially positive carbon, transfers here. That's the first step always, right? Well, actually, attack partially positive carbon there. Then what happens is, well, then I've got this carbon, oxygen with a lone pair of electrons negatively charged. We've got the Cl here, you've got your COCl, and then you've also got your now it's getting complicated because it's with these type of compounds, organic compounds. You've got your Cl there, then you've got, we've just added it on, right? So you've got your hydrogen, sorry, your oxygen, positive charge, and your hydrogen, and then something like that. H, something like that. What happens once we form the double bond? C-cell bond must break, and also what happens is that it goes from the middle of the OH to the oxygen, like that. There you go. So first step, pretty easy. And then lone pair of electrons once through form the double bond, C-cell bond must break, and that's obviously bonded to it. The oxygen's positively charged and it's bonded to it, and it's got the hydrogen attached to it as well, and then it just goes from there to there, and you lose that H plus sign. So that's why chemists usually just aim to design production methods with fewer steps with a high percentage atom economy. Less energy use slash better yield, high percentage atom economy, less waste slash pollution. Less energy use, better yield, less waste slash less pollution. Say why the ozone layer is beneficial for living organisms. Absorbs harmful UV radiation. State how chlorofluorocarbons form chlorine atoms in the atmosphere. The Cl bonds are broken, and want to be even more specific, homolytically. Give equations show how chlorine catalyzes decomposition of ozone. Cl dot plus O3, arrow ClO dot plus O2, ClO dot plus O3, arrow 2O2 plus Cl dot. They really like asking this question, give equation of this. It literally is copying, like with these, if you look in the spec, these two equations are literally on the specifications. The spec is literally telling you memorize these equations, and yeah, that's what you have to do for that. And then it says hydrofluorocarbons have been used in place of CFCs. In a mechanism to make a hydrofluorocarbon from fluoroalkane, two incomplete steps are shown. Give the name of the type of step shown by both of these equations. Okay, so absorption there. Well, obviously I've got the chlorine free radical plus what, right? Really, fluorine free radical plus the CH F2. It has to be that because this chlorine free radical there, what's remaining CH2F2. There you go. Then you get that. Then what happens is then you've got your CHF2Cl. Well, yeah, plus your Cl dot. Actually, it'd be better if I do CHClF2. Type of step, propagation step. That's pretty simple. Propagation step. So let me go through this again, actually. So it says name the type of step for both of these. Also, it's going to be propagation. And in propagation, firstly, I've got a chlorine free radical plus what? Well, to find out what plus is just going to be the CH, but I've got two of them because of the HCl, H2F2. Then I get that, then I add extra chlorine, then what do I get? CHClF2 plus your chlorine free radical. Propagation. Question 10 suggests whether 1 centimeter cube added to an X of this. Sodium hydrogen carbonate solution neutralizes the acid, so stops the reaction. Sodium hydrogen carbonate solution neutralizes the acid, so stops the reaction. Suggest whether order this reaction with respect to propanone can be ignored in this experiment. Concentration of propanone is much larger than the concentration of iodine. Yeah, definitely. Look at that. 25, 1, 25, 5.0 times by 10 to the power minus 3. Yeah, that's concentration of propanol is much larger than concentration of iodine. Hence, the concentration of propanone is almost constant, hence can be ignored. So, 10.1 sodium hydrogen carbonate solution neutralizes the acid. Sodium hydrogen carbonate solution, so it stops the reaction. Concentration of propanone is much larger than concentration of iodine. Hence, concentration of propanone is almost constant, therefore can be ignored. Use results in table 5 to draw a graph of volume sodium thiosulfate solution against time. Draw a line of best fit. So you're gonna have a volume 1, 2, 3, 4, 5, 6, 0, 1, 2, 3, 4, 5, 6, 7. Let's say 7, and then your thingy, your volume, add up in 5s. 5, 10, 15, 20, 25, 30, and 35, 40, 45. And remember, your graph has to take up, plotted points must take up at least half of the grid. And then you just plot it. 1 at 41. 2 at 35. 3 at 24. Yeah, 3 at 24. 4 at 22. 5 at 16. 6 at 10. And then you just draw a straight line. Draw a line of best fit. Here. Guess you could go, yeah, here. Yeah, just to draw a line of best fit, really. Explain how the graph shows the reaction is zero order with respect to iodine, the reaction between propanone and iodine. The idea, firstly, the statement obvious. The graph is what? It's a straight line. The graph is a straight line. Is a straight line slash constant gradient. So the rate of reaction does not change as the concentration of iodine changes. So the graph is a straight line, so that therefore has a constant gradient. So the rate of reaction does not change as the concentration of iodine changes. Graph is straight lines, therefore has a constant gradient. The rate of reaction does not change as the concentration of iodine changes. And then question 10.5, Arrhenius equation can be written as this. Use figure 8 to calculate a value for the activation energy E in kilojoules moles per power minus 1. First thing I would do again, the graph is a straight line. It has a constant gradient. Therefore, the rate of reaction does not change as the concentration of iodine changes. That was for this part. But in this part, straight line, y equals mx plus c. Compare it to that. Y is ln k. Gradient is minus E over RT. So gradient equals minus EA over RT. I want to find out EA, therefore minus EA equals gradient times by RT. R is 8.31. What's T? What's T? Oh, T is X. So I don't care about T. The gradient is minus EA over R. Yeah, so that would be a massive mistake if I did that. So yeah, because X has got to be something, X in this case is T. Therefore, all I need to do now is just find out the gradient and then times it by R, which is 8.31, right? So let's do that. Look at the gradient. Let's go here. Let's zoom in a bit. How do I do it? Can I do a straight line? I don't think I can do that. It's fine anyway. So here, that point there, and here, that point there. Perfect. Then I do the gradient. So I'm going to do minus 14.2 minus 2.8 over 0.0018 minus 0.0012. I get minus 21,923. Do my answer times by 8.31. That's that. Divide by minus 1. That's the gradient of EA. But activation energy is measured in joules, right? And I want it in kilojoules. Therefore, I need to divide my answer by 1,000. And then I get 182. Perfect. Kilojoules multiplied minus 1. So, compared to y equals mx plus c, therefore gradient is minus EA over RT, right? No, x is equal to t, therefore gradient is minus EA over R. Rearrange to get minus EA, gradient times by R. How do you find gradient? Y2 minus y1 over x2 minus x1. I just did this, that point there, minus that point over this point minus that point. Y2 minus y1 over x2 minus x1 times by R, and then negatives cancel out, and then divide by 1,000 because you want in kilojoules multiply minus 1. And activation energy is measured in joules. And that is the end of the past paper.